My name is Ray Ding, and I present BitSense universal and nearly zero error optimization for sketch counters with compressive sensing, which I worked on with Shibo Yang, Xiang Chen, and Qun Huang at Peking University. Measurement is crucial to network management. With the support of modern programmable switches, sketch-based network measurement becomes popular. It deploys sketches on switch, which measure predefined flow statistics. The control plane periodically collects these sketches and reports flow statistics to management tasks. Here is a generic view of sketch. It consists of arrays of fixed-size counters. Moreover, it supports at least two operations. The first is updating with a packet. In measurement jargon, a packet is represented as a flow key plus a packet value, whose definition is application-specific. The update operation hashes a flow key to select counters and add the packet value to these counters. The second operation is querying of flow statistics. It hashes the flow key to multiple counters and combines their values to yield an estimate. The strengths of sketch are twofold. First, it achieves high accuracy in limited memory space. Second, it incurs low computation and access overheads. However, on-chip memory becomes a bottleneck for sketch deployment nowadays. There are three causes. First, high-speed switches have limited RAM due to power and speed constraints. The equipped memory is typically within 100 megabytes. The second cause is the rapid traffic growth. According to Cisco, there is a 25% annual growth rate in global data center IP traffic. Thus, sketch requires more counters to maintain accuracy. Third, co-located functions consume more and more memory. For example, part of the RAM is allocated to match action tables and stateful objects. Part of it is reserved by the switch itself. Thus, the memory budget for a single sketch is extremely tight. In answer to the memory bottleneck, we focus on counter compression. The motivation is that sketch counters contain implicit waste, which is justified by two observations. First, counters must have enough bits to avoid overflow. For example, if a value exceeds 2 to the 8th power after updates, an 8-bit counter overflows to 0 and induces large error when queried. Thus, at least 16 bits are required in this scenario. Second, most counters have small values and do not need higher bits. To illustrate, we test the counter distribution on multiple sketches. It is always skewed toward 0 due to traffic skewness and hash conflict. Unfortunately, naive approach do not work. One may think of using different lengths of counters. The drawback of this method is that the minimal counter length required is unpredictable unless you know the future traffic. Also, it incurs prohibitive addressing mode. In a second try, we hope to use fewer counters of longer lengths. However, it sacrifices accuracy as a result of more hash conflicts. Previous research proposes two methods. The first is to adopt variable length counters. Specifically, it begins with short counters and elongates them on overflow by merging with adjacent counters. This idea is of course intuitive. However, it incurs formidable addressing overhead, and it is not universal, since merging can break the data structure of some sketches. The second one is by counter sharing. Specifically, part of the counters share a common physical address. It leverages decoding methods to restore counters. However, it incurs severe accuracy drop due to lossy compression. Now we introduce our work, BitSense, whose primary features include memory efficiency, universality, nearly zero error, robustness, and user-friendliness. The architecture of BitSense is as follows, which consists of 4 steps. Step 1 is that users develop sketches with the BitSense counter interface. The interface creates an abstraction that the users are manipulating fixed-size counters so that they don't bother with low-level details. Step 2 is that the compressed or transformed sketch is dispatched to the data plane. It consumes far less memory than before. Step 3 is that the packets update the transformed sketch via the interface, which ensures the same semantics as before. The last step is that the control plane periodically collects the sketch and restores it via decompression. It results in a store that is isomorphic to the raw sketch. Now the sketch is ready for query. Let us focus on the key idea of compression. Specifically, BitSense represents a sketch counter using several shorter segments. The picture shows an example of representing each 24-bit counter with 3 8-bit segments. We organize these segments in different layers according to their position. Now, each segment holds the overflow value of a lower segment. Note that due to the skew counter distribution, higher segments are mostly zero, the bars. We design a hash-based compression scheme. First, we reduce the number of segments in higher layers. For example, instead of 6 layer 1 segments, we use only 3 segments. Accordingly, the overflow of a segment S will be stored in k higher segments. These higher segments are chosen by applying k distinct hash functions to the index of S. So, how do we decompress these segments with minimal error? The answer is by formulating a constraint optimization problem. It has 4 ingredients. First, its priority is the sparsity, which suggests us to find sparse solutions. Second, the constraint is imposed by hash maps. We must find solutions subject to these constraints. Third, the input is segment values of a higher layer. And finally, the output is the restored segments of the current layer. 2 ingredients are crucial to ensure nearly zero error decompression. The first is a compressive sensing-based optimization goal that is suitable for restoring sparse vectors. It filters out plausible but unlikely solutions. The second is a lightweight data structure that marks non-overflow segments. It further shrinks the solution space. We prove theoretical result that guarantees its accuracy. The key result is that as long as the number of higher layer segments is at least 1.09 times that of the actual overflows, decompression achieves zero error with high probability. Here is an example. Suppose layer 0 has 10,000 segments, but only 10% of them overflow. Then layer 1 only needs 1,090 segments instead of 10,000 to ensure almost perfect decompression. There are other important designs that enhance BitSense. Due to the time limits, we only give a short list and invite you to read the paper. BitSense further supports real-time data plan counter estimation by a lightweight auxiliary sketch. It also supports complex operations by composing basic interfaces. Besides, BitSense supports P4 architectures because of acyclic data dependencies. Finally, it has an efficient auto-configuration scheme based on tight threshold results. Our results show that BitSense achieves high accuracy and low overhead. First, we demonstrate the resource usage measured on a Tofino switch. Only 9 megabytes of RAM are available for sketch algorithms. We compare the resource usage with and without BitSense and their differences on 3 representative sketches, namely CountMe, Sketchlen, and Unimon. We find that RAM is a bottleneck, and BitSense reduces by at least 10 to 4% of the total amount on switches. Meanwhile, BitSense incurs low overhead on other resources like memory access, pipeline stages, and so on. The next results show that BitSense improved the performance of existing sketches. Here, we test the accuracy of flow size estimation. Our workload contains both the Kata trace and the data center trace. Following the measurement convention, we use ARE and flow ratio to show the accuracy level. A lower ARE is better, while a higher flow ratio is better. We present the result on 6 sketches here, where we obtain 2 findings. First, BitSense attained the same accuracy level with 25 to 50% less memory. Second, given the same memory budget, BitSense reduces error by orders of magnitude. Besides, evaluation of BitSense on other measurement tasks demonstrate the same conclusion. More results can be found in the paper. For example, it includes the robustness result of BitSense when integrating with heterogeneous sketches and mirroring differently skewed traffic. It also includes the optimality result, showing that BitSense outperforms the SOTA solutions. To recap, we first identify and quantize the amount of implicit waste in sketch counters. Motivated by the implicit waste, we designed the BitSense architecture with universal and user-friendly interfaces. Next, backed by theoretical and experimental results, the compression scheme achieves nearly zero error. Finally, we present a P4 implementation and perform thorough evaluation to show that BitSense achieves high accuracy with limited overhead. Thank you.